In this video, we are going to study regarding the design of continuous slab. Already we have seen the design of continuous beam. Based on similar guidelines, we will try to design this continuous slabs also. So let us see. So in case of T-beams and slab floors, the slab is continuous over T-beams spaced at a regular interval of around 2.5 to 3 meters generally. Continuous slabs are designed similar to that of continuous beams using moment and shear coefficients recommended in IS 456-2000. Already in the previous videos we have seen how to design a continuous beam using moment and shear coefficient which has been given in IS 456-2000. So same thing we are going to use here also. The depth of the slab is defined based on span to depth ratio, which is 26 for continuous beams or slabs. Then next is the limitation regarding variations in the span and redistribution of moments discussed in the continuous beams also apply for design of continuous slab. That means what all things earlier we have discussed in the continuous beams, like the length should not be varying more than 15% of the longer length. So same thing we can apply for the continuous slabs also, and we can use the moment and shear coefficient which is given in IS 456 so as to design the continuous slabs. So let us try to design one continuous slab. Design a continuous one-way slab for an office floor. The slab is continuous over T-beams spaced at 4 meters interval. Assume live load of 4 kN per meter square and adopt M20 grade concrete and Fe415 HYST bars. So data given is live load, that is 4 kN per meter square they have given. M20 grade of concrete they have given, and Fe415 steel they have given. The next is, let us try to fix the depth of the slab. Since the slab is continuous and the percentage of reinforcement is small, so therefore we can have a span to depth ratio may be assumed as like which is given as 26 in the code, we can have it as 30 also. So therefore L by D ratio you can take it as 30. So therefore depth will be equal to span divided by 30. Span is 4 meters divided by 30. So approximately we will be getting answer as 134 mm. So let us adopt an effective depth of 140 mm and overall depth of 160 mm. Next, let us try to calculate the loads. So self weight of the slab is equal to 0.16 is the overall depth multiplied by the density, that is 25. So we will get answer as 4 kN per meter square. So let us assume a flow finish of 1, and therefore the total dead load will be equal to 4 plus 1 5 kN per meter square. So that we'll try to write it as G. Why? Because while calculating the moment using moment coefficients, so we are having different coefficient for dead load as well as for the live load. So therefore here we have not clubbed both the dead load and live loads, we have calculating separately. So further I'll tell you, based on the coefficient we'll be calculating the moment due to this dead load separately and live load separately. So live load given is 4 kN per meter square. Next is regarding the effective span, which is nothing but center to center of the supports, that is L is equal to 4 meters. Then next is we have to calculate the moment and shear forces based on the codal provisions which is being given in table 12 and 13 of IS 456-2000. So if you refer IS 456-2000, which is given in page number 36, they have given table number 12 they have given bending moment coefficient, and the table number 13 they have given shear coefficient. So for dead load we can use this coefficients, and for live load we can use these coefficients. So if you see now, so one thing what we can observe here is, so when we are calculating the span moments, if you compare the coefficient, this is 1 by 12 which is greater than 1 by 16, and if you compare this for live load 1 by 10 which is greater than 1 by 12. So therefore if you want to calculate the maximum moments, so we can use this coefficient. Why? Because this is more, so therefore what values we'll be getting will be maximum itself. Again, we need not calculate for this. Similar for support moment also, if you see this is 1 by 10, this is 1 by 12, so therefore this is more, so therefore moment what we'll be getting will be more. Similarly here also, that is 1 by 9 and this is 1 by 9, same, no problem. So based on this, let us try to calculate the moment. This is for dead load and this is for the live load. So therefore negative moment, so negative moment means support moments, we'll try to use this coefficient, that is 1 by 10 and 1 by 9. So negative sign what they have written, this is just an indication to show that this is a negative moment. That is we have a dead load, that is G, and Q as a live load. That is for dead load, if you see coefficient is 1 by 10, so we have 1 by 10, and for live load it is 1 by 9, so it is 1 by 9. And so therefore we are going to have this as WL square by 10. So W is nothing but G what we had given for dead load. So therefore dead load total load was 5 into L is 4 square divided by 10, plus we have live load, that is Q, that is 4 kilonewton already which is being given, into 4 square divided by 9 multiplied by 1.5, so as to get the ultimate moment, that is negative moment. So in the table if you see, they have given a negative sign which indicates only the negative moments. So if you calculate, we'll be getting answer as 22.66 kilonewton meters. Then next is we'll try to calculate the positive movement. So for positive movement means like for span movements, we'll use this coefficient. For dead load it is 1 by 12 and for live load it is 1 by 10. That is 1 by 12 for dead load and 1 by 10 for live load. That is GL square by 12 and QL square by 10. So therefore G is 5 multiplied by 4 square by 12, Q into L square, that is 4 into 4 square by 10 multiplied by 1.5. So you'll be getting answer as 20.65 kilonewton meters. This is the maximum what we can get positive and negative moments. Then next let us try to calculate the maximum shear force. So we have to refer table number 13 for shear force coefficient. So if you see at support it is dead load it is 0.4, and if you see this is the maximum what we can have, therefore we will use 0.6 multiplied by dead load plus live load multiplied by L, that is 5 plus 4, L is 4 multiplied by 0.6 we have, which is multiplied by 1.5, so as to get the ultimate shear. So we'll be getting answer as 32.4 kilonewtons. So let us try to check the depth required for the maximum moment, that is MULIM is equal to 0.138 FCK BD square. So therefore D required will be equal to M, that is maximum what we have 22.6 out of these two. So therefore 22.6 into 10 raised to 6 divided by 0.138 FCK BD square. So B will be 1000. So if you calculate, depth required will be 90.6, which is less than 140 mm. So therefore what depth we have provided is safe. Then next let us try to provide the reinforcement based on the moments what we had calculated. So moment is 22.6 into 10 raised to 6. We can use that formula, that is AST is equal to 0.5 into FCK divided by f of I into bracket of 1 minus square root of 1 minus 4.59 into mu divided by FCK BD square. So in that formula also if you substitute, you'll get the answer. In this also if you substitute, you'll be getting answer as 485 mm square for a moment of 22.6. So if you are going to provide a 10 mm diameter bar, we have to calculate this spacing. So it is being calculated as spacing will be equal to area of the diameter of the bar which is provided, that is pi by 4 into 10 square divided by 485, that is AST required, multiplied by 1000. You will be getting answer as 150 mm approximately center to center. So if you provide 150 mm, the AST provided will be, similarly if you calculate, AST provided will be 544 mm square. So as our moment is approximately same itself, so 20.66 we have. Therefore, the same reinforcement can be provided for the positive mid-span moment also. So for negative it is 22.6, positive it is 20.65. These are approximately same. So therefore, we can provide the same reinforcement at mid-span as well as near the supports. The next is regarding the distribution steel, that is 0.12 percentage of B into D, that is B is 1000, D is 160, so therefore minimum required will be 192 mm square. So therefore for this we can provide a distribution steel that is 10 mm die about 300 mm center to center. Then next is usually what happens that the slab is going to pass a shear check. So therefore, let us check tau v is equal to Vu by B into D. Vu is 32.4 into 10 raised to 3 divided by B is 1000 multiplied by D is 140. So we'll be getting answer as 0.23 Newton per mm square. So if you refer table number 19 of IS 456 and if you interpolate the values, we'll get tau c which is 1.25 multiplied by 0.36 which is 0.45 which is greater than tau v. So therefore slab is safe against the shear. Then next is we have to check for deflection. So same formula, L by D maximum is equal to L by D basic multiplied by KT, KC and KF. So here KC and KF will be 1, only KT value we have to calculate. So as to calculate this KT value, we have to calculate the percentage of steel provided, that is EST provided divided by B into D multiplied by 100. So we'll be getting percentage of steel as 0.37. If you refer the IS code, we'll be getting KT value as 1.35. So therefore L by D maximum will be equal to, we can use 26 divided multiplied by 1.35 which will be get approximately like greater than 29.9 itself. So therefore L by D provided, what we have provided is 4 by 4 meter by 140, that is we'll be getting 28.5 which will be greater than this value what we had calculated. So therefore what we can see is the slab is safe against the excessive deflection. Then next is we have to do provide the reinforcement detailing also. So already how to do the detailing of this continuous slab already, I had covered this in a video which says about use of SP34. In that video all these details like what all distances has to be provided already I had covered in that video. For more detailed references you can refer the videos which shows the detailing of a continuous slabs or beams. The next is the main reinforcement what we have provided, that is span moment and as well as the negative for negative moment support moments we have provided same reinforcement, that is 10 mm dia about 150 mm center to center. So this is the main reinforcement span moment, and this is for the negative support moment, that is 10 mm dia at 150 mm center to center. So what we can do, we can provide the alternate bent up bars. You can provide alternate bent up bars. So we'll take 50 percentage of the reinforcement at the top, it is AS1 what we have here. Similarly AS2 we can calculate 50 percentage of bent up can be done here. Then next is the span is center to center is 4 meters. So from the center of the support till this bent up it will be 0.15 L, and from the interior support it will be 0.25 L1 as this one is L1. Similarly on this side it will be L2 as this distance will be L2, that is 0.25 times of L2 we have. Then next is top reinforcement. Here this extra projection what we are going to have, so this will be like 0.3 times of L1 as this is L1 and 0.3 times of L2 as this is L2. So depth of the slab is overall depth is 160 mm. So in this way we are going to do the detailing, and if you see the distribution steel what we had provided, that is 10 mm diameter 300 mm center to center. So here also if you see the reinforcement what we have provided, that is the distribution steel which is 10 mm dia about 300 mm center to center.